welcome to the second lecture of the week, um, or maybe the third, excuse me. But this is our Gamma Ray week for the MTV Summer School. So thank you again for joining. Thank you to those who joined yesterday. But without further ado, I'm going to go and hand it over to the lecturer today to tell you a little bit about gamma ray detection.
Yeah, thanks, Skylar. Hi, everyone. My name is Peter Hotvet. I am a third-year PhD student at the University of Michigan, where I study radiation detection. I work specifically with cadmium zinc telluride radiation detectors, and if you don't know what those are, you will soon. I promise you that much. I'm excited to share with you today some topics related to gamma ray detection. I'm going to tell you up front that there are a lot of slides to get through and I only have an hour, so I'm happy to answer your questions if you put them in the Q&A. Please note that if you've asked more than one or two, I may end up prioritizing other people's questions, but I'm excited to answer your questions. I'd be happy to answer them in post in an email or other communications if you have them. So, with that in mind, I also want to make it clear that today's lecture is going to be more exploratory with regards to the concepts rather than being more technical. They're going to be a more broad overview. And what do I mean by this? Well, you'll see in just a moment. And I see also as well, what is the background pic of the first slide? We'll talk about it. Don't you worry, anonymous attendee. So I'm going to give this talk for the Nuclear Engineering Summer School for 2024, and these slides are adapted from Bakari and Lopez. So if you have seen this lecture before last year, very similar, little different. So we're going to go over some contexts and some applications of gamma ray detection. And we're going to talk a little bit about detector types and classifications. And then I'm going to get into some specific examples of specific radiation detectors we might use on a daily basis in the lab, in the field, whatever they may be. And again, just a reminder, if you have your hand up, I'm not going to be able to answer it. Please ask all your questions via Q&A. So with that in mind, let's begin with the beginning. We have Uranus and Gaia. These are Greek people in Greek mythology. Uranus is the god, Greek god of the sky, and Gaia is Mother Earth. And yeah, I know it's weird. Why are we talking about Greek mythology? Why are we talking about Tartarus right now and the underworld of the Greek mythology? Why are we talking about this? Well, as it turns out, Uranus just happens to name one of the most important elements that we want to detect using our radiation detectors, uranium. It comes from Uranus. It comes from the Greek god of the sky, and of course the planet as well. In case anyone was curious about that. Similarly, the ruler of the underworld is Hades or Pluto, and you've got our guy Cerberus over here. Look at him, all three heads of him and everything. He's missing an arm, but yeah, that's what happens sometimes. And Pluto happens to be the name of another very important element that we want to be able to detect, plutonium. So this is just like your very first world context of these two elements. And these elements are elements that we want to be able to detect with gamma ray detectors, among other things. So, right now, I would encourage you to think about gamma ray detection and its applications. I want you to think to yourself, maybe take 30 seconds on a piece of paper you have right next to you and just write down all the things, applications you can think of why we would want to detect gamma rays. I will give you that time. I want you to take this time right now and just write as many as you can in the next 30 seconds, starting right now. And in that time, think about, there's obvious situations, of course. There's some ones that maybe you don't think of. I'm not going to be asking you to post your lists. This is entirely for your own reference to see where you are at the start of this lecture and where you are at the end of this lecture. I want you to be your own judge here. I think it's important for you to gauge your own learning and understanding, especially in a summer school like this. So we'll go about 10 more seconds. All right. So, gamma ray detection applications, the obvious one that you might think of when we think about nuclear power and nuclear energy is accident scenarios. If something bad happens at a nuclear power plant, we want to be able to know. We want to be able to say that we know what's gone wrong here, and we want to be able to point to it and say, this is what has happened. So if there were, say, a leak or a spill, that's really important. We want to be able to measure it. And if it's radioactive, odds are we can find it with gamma ray detection. And if we can't, then we can use a different type of detector. Similarly, if a source, just a general radioactive source, goes missing in some capacity, we want to be able to find it. So, source localization is just as important because we are able to find radioactive sources by measuring the gamma ray flux, basically. The magnitude of the gamma rays that we measure, where we find them, and at what energies they are. And similarly, we could do environmental monitoring with this. So, for example, maybe there's not a spill anywhere, but you want to measure the radon in your house. If your house has a basement, you want to be doing regular checks of radon levels to make sure that they're not too high. This is one of those ways that we can determine that with gamma ray detection. We can also do source characterization for safeguards and treaty verification. So if we have a country that's claiming, hey, we're only going to enrich our uranium this high, we can verify that through gamma ray detection. As it turns out, uranium 235 and uranium 238 give off photons of different energies. So we can use gamma ray detection to verify these claims. And that's probably one of the most important ones that MTV really cares about. But global safety and security is not the only reason you would measure gamma rays. You can also use them for medical applications, like in radiotherapy and in medical imaging. When you get an X-ray at the dentist or something, or a CT scan, you're doing radiation imaging, and that's done through using gamma rays. And then lastly, you've also got your space applications. We all love space. Space is great. We exist in it. And sometimes we're curious about what is out there beyond us, right? And so if we have, say, gamma ray bursts that happen, we want to be able to not only measure them, but know where they come from, maybe what caused them. We can do that by measuring the gamma rays. Now, I want to be very clear, first and foremost, that I am going to be using some terminology interchangeably through this lecture. I'm going to say photons more than gamma rays or X rays. Photons is a more umbrella term that sort of captures it better, in my opinion. Though, X rays are made from sort of photons from electron interactions, and gamma rays are made from nuclear events. So, in case people want to, get on me for that, there you go. There's my disclaimer. So, we're going to talk next about the radiation detection process. There are two types of radiation. There is directly ionizing radiation, and there is indirectly ionizing radiation. And these directly ionizing radiation particles are charged particles. These are alpha particles, beta particles, and heavy ions. When I say betas, I'm mainly referring to electrons here, just for clarification. And then we have uncharged particles, which are neutrons and gamma rays. Now, the thing we have to know about radiation's interactions with matter is that when charged particles interact with matter, they create direct ionization. That's the big word, is ionization. It's making ions. It's removing electrons from atoms to ionize them. So in this case, for betas, you might be making for all of these, you might be making electron ion pairs if it's a gas, or you might be making electron hole pairs if it's a solid. What do I mean by this? I mean, if you have a crystalline structure and you knock off an electron, you're removing something from the lattice, creating a hole. It's sort of a fake positive charge. Now, that's great. That's what the charged particles do. The uncharged particles, like neutrons and gamma rays, are not necessarily creating ionizations. Instead, they interact with matter via nuclear reactions and other photon mechanisms. If you went to Skylar's talk yesterday, you might know what those mechanisms are. But these mechanisms then create sort of secondary charged particle interactions in matter, which therefore can be measured. So we're using the responses of these uncharged particles and their interactions to determine if they're present or not. It's kind of like sensing ghosts. It's a little tricky, but it's quite fun. I really enjoy it. And so after we have these interactions with matter, there's a response, and basically we're taking the current, usually, of the movement of the electrons and ions, or electrons and holes, and converting them via an analog to digital response to create waveforms. Now, these waveforms kind of maybe have a pulse and then they go down like that. You'll see some sample ones later on in the talk. But the idea is that from those waveforms, we can determine information about the radiation interaction that occurred, whether that's the energy of the photon, whether that's the time it took place, the particle type in case it wasn't a photon, or what type of interaction took place. So there's a lot that we can do just from very simple interactions with matter. And it's very, very cool. This really inspired me a lot when I was just, first learning how much we can learn from a waveform. And so again, Skylar probably talked about this a little bit, but I'm just going to cover it again. Photons interact with matter in a variety of ways. X and gamma rays may interact in a bunch of different interaction types, presented in this list here. As we go down the list, the energy it corresponds to the energy of the incident photon. The big three that we're going to focus on in this talk are the photoelectric effect, the Compton scattering with inelastic scattering, and pair production. These are kind of the big three we care about. Photonuclear reactions are pretty high energy. Rayleigh scattering is like almost negligible energy. So we want to be able to measure exactly when these things are happening. So when we have these, we have what is called a total photon cross section. And this is just the probability of a given photon interaction occurring. So on our horizontal axis here, we have the incident photon energy in MeV, mega electron volts. And on the y-axis, we have the z of the element in which the photon is interacting. So if we are working with lead, for example, a high Z material, and we are working with a 100 keV or a zero point 0.1 MeV photon, that interaction is going to be more likely to be a photoelectric absorption. However, if that photon is instead 1 MeV, it is Compton scattering, more likely to Compton scatter. And if you get even higher up in energy, like 10 MeV, then pair production really dominates here. And if we want to characterize that for a given material, we can do so by adding the total photon cross section for each one. This is just a probability of things occurring. So you'll see here for lead, as we increase the instant gamma ray energy as a function of energy, we can observe the probability of each interaction occurring. This blue line is the total cross section, meaning that if you take all three of these lines here and added them all up, you would get this blue line here. So at lower energies, you can see that the photoelectric effect really dominates. But as we get to about 1 MeV, the Compton scattering is more prominent here. And as we get closer to 10 MeV, we reach the pair production dominating. So all of these here provide a very meaningful understanding of what it is that is happening or could happen in the material that we are using. Now, that's really important because this is going to infer materials that we can use to measure photons, right? Because if they're interacting in the material, we can measure them. It's just knowing how. So I'm going to move on now to gamma detectors and their classifications. If you do have questions at any point, please put them in the Q&A and I will be able to respond to them as they come in. So there's a lot of different gamma detectors, and we're going to classify them. First is these ionization detectors. These are ionization chambers, proportional counters, and Geiger-Müller detectors, cloud and bubble chambers. These are primarily gas-based. We're going to talk about these first, but there's some other ones I want to talk about as well here really quick. There's these luminescent detectors, which are thermoluminescent or radio photoluminescent. So if English is not your first language, this might look like a lot of letters all in a row. It's a lot, I understand. But basically, it's just photoluminescent detectors that measure radiation. We next have scintillation detection detectors. These are detectors that give off light when an ionizing radiation event is deposited inside of them. We'll talk about these a little bit as well. Then there's semiconductor detectors, which there's a lot of those as well. And I work with semiconductor radiation detectors, so I'm happy to talk about these in a little bit detail near the end of the talk. We have chemical detectors, which are photographic emulsion detectors. These are like film almost. Like if you took a photo on a piece of film, that's kind of what these are like. And then you have activation detectors, which are like dosimeters of sorts. And just a reminder, if you have questions, you need to put them in the Q&A. So let's talk about ionization detectors first. How are scintillation detectors different from luminescent ones? We'll talk a little bit about that. The short is that scintillation detectors give off light, whereas these luminescent detectors are more optically stimulated. So they are more optically, light interacts with them more. That's the gist of it. We don't really work too much with luminescent detectors as much, but they do exist. So first, gaseous ionization detectors to the anonymous attendee who asked. We're going to talk about these cool shapes, starting with a cloud chamber. So, this is a cloud chamber, and this is a uranium rock. And as you can see, you've got these misty vapor like things coming off the rock. If you've never seen a cloud chamber before or don't know what's going on here, I'm about to explain it to you. But it's very cool. I mean, you can see that from this rock, things are just shooting off in all directions, and they stay visible for quite a while. What's going on here? Maybe think about like how this is possible. Well, I'll tell you. I'll tell you how it's possible. This is a cloud chamber, and the way that cloud chambers work is it consists of a sealed environment containing a supersaturated vapor of water or alcohol, and an energetic particle coming off of the uranium, like radioactively decaying, essentially. This could be like alpha particles or beta particles, or maybe it's a gamma ray depositing its energy. Um, is entering, it interacts with the gaseous mixture, knocking off electrons off of those gas molecules, resulting in a trail of ionized gas particles. Excuse me. Excuse me. And the resulting ions act as these like condensation centers where that mist trail sort of comes from. And so these droplets are visible as a cloud track that persists for like several seconds. And I really want to emphasize several seconds is really important here. Because eventually we're going to see that for modern radiation detectors, the order of time uh, in which we would detect these radiation events is on the order of like nanoseconds. So the fact that this is visible for several, like 7 seconds, you can see it right here. So we're gonna move along here, and then these tracks, they have characteristic shapes. For example, an alpha particle track is sort of thicker and straight, whereas a beta particle track is wispy, and it shows more evidence of deflections by collisions. I have a question. I think that question's a little bit beyond the scope of this talk. The question really is, why is it impossible for the nuclear power plant reactor to turn impossible, excuse me, to turn into an explosive? It has to do with the fuel. Again, that's beyond the scope of this talk. I'd be happy to answer it later. Thank you. So you have the shape here, right? And you're going to have a gamma ray come in, and you have this gamma ray entering this medium, this gaseous detector, and it's going to, again, sort of create an interaction. I have a question here, real quick. I think it actually is really important to address here. How do you know which detector to use? Does it depend on the material you are analyzing? It depends on lot. It depends a lot on your application and how you want to measure the radiation. Do you care about the energy of the photon? Do you care about where it came from? Or do you just want to know if it's present? That's kind of the idea, is you want to be able to think about why you're measuring it, like the main application. So to return to this, if we have a gamma ray that enters and it interacts kind of at this knot point, let's say it sort of pair produces with a recoil electron. If this were left to its own devices, the electron here and the positron here would deflect and sort of make this spirally shape. It would scatter off of the remaining electrons in the medium. And then this recoil electron would sort of travel along its own path. However, if we were to have a pair production with a magnetic field applied and have sort of an electric and magnetic field applied, then we're able to very easily control the paths of these electrons and positrons, or the ions as well. So that is the idea behind ion chambers. Um, so there's that. What is a recoil electron? I'm glad you asked. The recoil electron is when a gamma ray enters the detector and it interacts, deposits some of its energy, and bounces off in a different direction. It has to bounce off something, and it bounces off that electron. So that's what I mean when I say a recoil electron. It's Compton scattering, for example. That's just one of many. So the ion chamber, its detector principle is very simple. It's a gas-filled space with two electrodes supporting an electric field that is applied by an external voltage source or a bias, so to speak. And the idea is that the gamma ray interaction creates charged particles. You have electrons and you have ions that have an energy proportional to the electric field applied. And so what we do is as the electron, there's an interaction, the electron travels through creating ions. We can measure the migration and the collection of the ions and the electrons, and the result is a measurement. Quick question I have: is there a standard unit specifically for measuring gamma ray radiation? That is complicated because measuring gamma ray radiation is a very broad topic. If you're looking for like dose, you have REM and you have Rankine. Excuse me, that's for exposure. Dosimetry is a whole field in and of itself. You'll see what we can do to really classify the measurements of gamma ray radiation. So what we have here is you'll notice that as we collect the electrons and the ions, one dependent variable or independent variable that we can change is the quantity of voltage applied to the system, which corresponds directly to the electric field strength. And that allows us to collect more or less charged particles. And that's really important for our different applications. Um, so building off the question that we had earlier, so the electron that is hit by the gamma ray ionizes the atom and not the gamma ray itself, right? So I won't talk too much about this just because this is sort of yesterday's talk, but the idea is that gamma rays can be absorbed when they have low enough energy. So if a gamma ray scatters enough times, it's going to continuously lose energy and then be absorbed by the material. What is the best detector for gamma rays? Radiation damage can damage DNA. There's a lot of different detectors that we can use, and I'm hoping that by the end of this talk, you'll be able to sort of get an idea of which ones might be best for specifically medical applications in particular. Um, so that's a good question to hold on to, I'd say. Okay, returning to ion chambers and the idea of the electric field strength. If we increase the applied voltage, which is on a linear scale, we will get an increase or a change in the charges collected. So again, this is on a linear scale and this is on a logarithmic scale. So the jump from this ion chamber region here to the Geiger region here is much, much higher. Just keep that in mind. So there's sort of three primary regions out of these six that are really usable for radiation detection. We have the ion chamber region, wherein we can use it for dosimetry purposes, where the number of alpha particles or beta particles, for example, um, are easily collected, right? And you can tell that there is an obvious difference between them. As we increase the voltage applied to this system, we also can therefore increase the number of charges collected. Specifically on the logarithmic scale, there's an obvious difference between these heavier charged particles and lighter charged particles. And that is called the proportional counting region, where you are able to determine a specific difference between the two particles interacting. However, you have to be aware of where your voltage is. After this region, you start to get a region where there's sort of this non-linearity between the two. And as a result, we can't really use it that well. And then once you get beyond that threshold, you sort of reach this region where everything is being collected and everything is happening at the same time, where you can't distinguish the alpha and beta particles, the lighter and heavier charged particles, but you are able to measure them and quite well. And that is the Geiger region. So if you've heard of the Geiger-Mueller detector, that is where that voltage is applied. And so in that space. And you'll notice that if you get any higher, then you start getting like constant electrical discharges, which is basically just noise and useless. So that is ultimately where we sort of stop with our voltage application. Now, again, the Geiger-Mueller counter, you've probably heard. Actually, good question. What amount of DC voltage is applied? I apologize for not having this on here right now. It's on the order of like kilovolts. Hopefully that helps. There is a text that will definitely be able to give you that number for sure, which I'd be happy to point you to at the end of the talk. But the Geiger-Mueller counter you have probably heard of before because it makes a noise. So if you've heard a Geiger-Muller counter clicking, that is sort of the electrical discharges you hear. Does the ion chamber use the same mechanism as the Bragg-Gray cavity theory? Yeah, kind of. The idea, I won't get into Bragg-Gray cavity theory too much. It's been a little bit since I've studied that myself, but the idea is very similar. Yes. So if we move along to the Geiger-Muller counter, specifically, we're looking at avalanche formations. So in this space, I want you to first make note that this is like a cylinder. This is a tube. So this outer wall here is the same one as this, and there's an inner anode wire. So if we have a gamma ray coming in here and ionizing the gas at some point right here, what's going to happen is that the liberated electron is going to be drawn toward the anode wire. However, as it does, it may ionize other electrons. And then those electrons might cascade and avalanche into other ones. And they might even create um, uh, the ion chambers are a detector. They are a broad, encompassing idea of a detector inside, and then there's a corresponding gas that you would use. So hopefully that answers your question. Are ion chambers in form of a detector material or a device? They are a device that contains a gas. The material would be more like the radioactive thing you're trying to measure. And so what might happen is you might create new photons, which could then ionize electrons, creating more paths of ionizing radiation. And then those might have more photons, which could create even more. And so you end up getting just these tons of secondary ionizations over time that if the electric field is so strong, you might create just avalanches throughout the whole detector to the point where for a single photon ionizing originally, you might get 10 to the 8th to 10 to the 10th more measured electrons being detected here. So that is something to keep in mind when you do that. And the discharge of almost entire gas volume can be read out via electronics or even a microphone at times. That's how loud this discharge can be. I have a question. Why can't we have one counter that will work on all the voltage ranges? We do. And so the thing is, the Geiger-Muller counters are explicitly operated in this region. That said, Geiger-Muller counters are one of many ion chambers. You can have an ion chamber that can operate in these regions, but there are some that are designed more practically for specific use in this region or in this region. So, this is going to be the end of the ion chamber bit. In the Chernobyl movie, the workers went into the reactor to detect gamma rays. Their headlights and other lights went up to the gamma rays. Can you explain that effect of gamma rays as well? That's some Hollywood magic, some of it with the headlights and flashlights. A lot of it has to do with the fact that there's just a lot of charged particles interacting, which can overwhelm electronics. But like the point where that was happening, dramatic effect, specifically the Chernobyl movie, has a lot of that, has a lot of accuracies, but it does have dramatic effects as well. We're going to move along to scintillation detectors now. The gas, once the gas is ionized, does the counter stop working? Yes, to some degree, which is why you do need to take care to consider how much a detector is used and if it's working. I'm going to move on here. If you want to know more information about these, I will send you the appropriate texts and you can email me. I do need to move on though. So we're going to talk now about scintillator detectors. These are detectors that give off light when there is ionizing radiation. There are two types. There are organic scintillators, which are scintillation light from molecular hydrocarbon bonds that are low density and have a low Z. And there are inorganic scintillators. And these scintillators have scintillation light from free electrons in a crystal lattice. And these have a high density and high Z. So when you think of organic scintillators, just think of plastics mainly. But there's more than just that. But that's kind of the idea. The way scintillators work is a gamma ray will come in. You're going to look at this and be hypnotized by this figure. It's a very enticing figure. And what happens is the light is the photon, excuse me, interacts and it sort of creates this excitation. And this excitation goes from ionizing radiation into light. The light then travels down the photomultiplier tube here and gets amplified a little bit and then it's read out by this VIR circuit here at the bottom. And the way that this works is it works differently for the different scintillator mechanisms. And this is where I'm going to tell you right now, it gets very complicated. So I'm going to very briefly gloss over the physics here. I do apologize. It is something that like I studied in depth for my qualifying exam kind of levels. The idea, though, is that the light signal collection, amplification, and conversion are the fundamental aspects of how scintillators work. And you have to be very careful with them because these sort of dynode stages are very carefully arranged and designed in order to maximize the collection of sort of your light, basically. So we'll start with organic scintillators. These are scintillators that use the bonds between hydrogen and carbon to sort of create that light from that excitation. And the way that they do that, there are two luminescence mechanisms via fluorescence and phosphorescence. Fluorescence is when you have your sort of absorption of the ionizing radiation, and then it immediately decays down to the ground state of energy of the crystal or the molecule energy levels. And this is fast. This is like on the order of like nanoseconds to microseconds. It's very quick. However, there's and it's primarily done through singlet states. Again, not going to talk about those here. Very, very complicated and beyond. I only have so much time. So that's the idea of the fluorescence. It's just an immediate drop down back to a ground state of the crystal or molecule levels. Phosphorescence is an indirect transition to the ground state via immediate energy levels. So you might have this excitation, but it activates a triplet state. And as a result, then it needs to reach this triplet state before it can go back down to a singlet state. That's what we say when we have phosphorescent occurring. And excuse me, this is slower. This is like on the order of milliseconds. So 10 to the 3, 10 to the 4 seconds versus 10 to the 6 to 10 to the 9 seconds. It's really important that you recognize, too, that light has different speeds depending on the type of radiation interaction in it, especially with these organic scintillators, to the point where the scintillation light from the molecular electrons from these hydrocarbon bonds creates a fast pulse decay. And because these are low density and low Z materials, they do have a low gamma ray detection efficiency, which is unfortunate. However, because they are low Z materials, they are quite good at measuring neutrons and alpha particles and these larger mass particles. And so what we can do is that if we measure this waveform here with our horizontal axis being time and our vertical axis being like light intensity, we can notice that the gamma ray tail of this waveform is much smaller than the neutron tail. And that allows us to do something really cool. If we integrate the tail, that is to say, we look at the area underneath the curve of these waveforms, we can classify particles. We can do what is called particle discrimination. So, pulse shape discrimination also is another term. So, as you can see by this plot, what we're looking at is we're looking at the energy in kilo electron volt electron equivalent, basically just the light equivalent measurement to keV. And we have the tail over total ratio. That is to say, the ratio of this tail integral to the total waveform. We can classify photons and neutrons in two different separate categories. It's very cool if you end up going into radiation detection for like non-proliferation work, or if you're working with like neutron detection, you will make one of these at one point. So I unfortunately cannot re-explain slide 23, but you can find it in text. At page 24, why is it better for fast neutrons and alpha particles? It's because those are larger charged particles or uncharged particles that have mass. So they're more easily, they interact with the material more easily. There's going to be a talk, I believe, about neutron detection going forward. So attend that one if you're curious. So we have various types of organic scintillators. We have these plastic scintillators, which are a solution of an organic scintillator in a plastic solvent. And these create very fast signals and are very flexible. They can be made into films, they can be made into sheets, they can be made into blocks, fibers. These are very easily scaled materials. They're easy to manufacture, they're easy to produce, they are plastics. They are, however, sensitive to organic solvents, so you have to take care to not expose them to those. We have liquid organic scintillators, which also have pretty fast signals, and they can be loaded very easily with other materials in order to influence the properties of the detector. So if you want to specify that you want to use a liquid scintillator for some application, you can do that by loading it with a different material. You just have to be very careful about impurities in the detector since these are very sensitive to that. Finally, you have organic crystals. These are like anthracene, trans, stilbene, naphthalene. These are fast signals, and all organic scintillators produce pretty fast signals. This is a little slower, 30 nanosecond levels. It's got a very high light output. Anthracene provides the highest light output of all the organic scintillators as of the making of like the original copy of these slides. They're difficult to handle, but they are very durable. And so, between their high light yield and their durability, they can be used for a variety of applications as well. That is organic scintillators. And next, we're going to talk about inorganic scintillators. And if you thought that the triplet states and all of those were a little complicated, this one's also very complicated. And there is a textbook that covers this, I promise you. Inorganic scintillators work on liberating electrons in a crystal lattice. That is to say, it is the band gap model. In order for there to be an ionization, the photon or the ionizing radiation needs to have a specific amount of energy that is greater than the band gap energy. What you're looking at here is just kind of an abstraction between the energy levels at the valence level of the electrons and the conduction level. Um, you don't need to worry too much about this diagram right now. The idea is that what we want to have in our material is sort of an activator. And this is an intentional impurity that makes it easier to jump the band gap, so to speak. The idea is that you're eventually going to jump that band gap and create that scintillation photon as a result of that ionizing radiation. And so, yeah, how do you decide between fluorescence and phosphorescence? We don't choose. That's just kind of a thing that happens in the detectors. Is it dependent on the atomic number or the analyte? It's that is complicated as well. It is not an easy thing. It depends a lot on the material that you're using. There's a lot of physics involved in scintillators here, and I you could do a whole lecture just on how scintillators work, how organic scintillators work, and then an entire lecture on inorganic scintillators. And I'm blasting through these in no more than like 10 minutes, so I do apologize. But the idea is that what you can do is again introducing like thallium into a sodium iodide detector to make it easier to create scintillating photons and that you can measure, and that's really really crucial. And so you might see like thallium doped sodium iodide. You'll see some other crystals I'm about to talk in just a moment. um, as we go, can a current be generated from the electrons pushed into the conduction band? Yes, that is exactly what we're trying to do. We're trying to measure a current output from that as well. However, sorry, my semiconductor brain hat is on. That's what happens in semiconductors. So keep that thought in mind. Is there any study on the absorption detection cross sections affected if the medium they are traveling through vibrating at different frequencies? Um, I think that just has to do with energy. I don't know quite what you mean by that question, so I'm going to say email me if you can develop that a bit more. So moving on, some examples of these inorganic scintillators. We have some crystals, some magic light emitting crystals. We have zinc sulfide doped with silver. Yes, you can email me if you have any questions beyond the scope. I will put my email in the chat at the end of the talk. We have zinc sulfide doped with silver, which produces a very high efficiency in measuring gamma rays because these are all high Z materials here. And it was used by Rutherford to create scintillation visible by eye. The problem with this one, scintillators has a very long decay time. It's far too slow for modern detectors. Um, Yeah, to answer the question, so scintillators are like semiconductors. The physics in how they create light versus how they create current is very similar, and you'll see why when we get to semiconductors. The way that they actually work is different. Um, yeah, the physics is similar but not identical. You also have sodium iodide detectors doped with thallium, which have a 0.23 microsecond decay time, so 230 nanoseconds versus 10 microseconds. That's, 100 times faster, which is really important. And because it's got a high Z material, this thallium in it, it's good at gamma ray detection efficiency. However, it is hygroscopic. What does that mean? It is sensitive to moisture in the air. And as a result, it needs to be shielded, or not shielded, sorry, bad word, needs to be protected from the outside elements. So we have to be very aware of that. But it's very commonly used. This is a detector that we see used in industry. We use it in the lab. It's very, very easily used. Question: what is the ideal energy range for exciting electrons in an inorganic scintillator detector? The range goes from, a couple keV. You can go low keV up to MeV. So 10 to the 3 to 10 to the 6 electron volts easily. Um, Lastly, we have cesium iodide doped with thallium. It's similar to sodium iodide, but easier to handle because it's less susceptible to thermal and mechanical shock, and it's less hygroscopic. However, it's more expensive. And the reason it's more expensive is because the materials like cesium and iodine and are not as easily sourced as sodium, for example. So you have to keep that in mind. Other crystals that we have include barium fluoride with intrinsic impurities. That's what's really important there, is that barium fluoride naturally has these impurities in it that make it very good at scintillating light, or very fast at creating that scintillating light. It has two sort of scintillation mechanisms. The first one working at 700 picoseconds, so 10 to the minus 12. And it has a slow component, slow, like 620 nanoseconds. And so that is good to use, but unfortunately, it's got very low light yield. So that is a trade-off. You have to consider if that's something you're willing to accept. How about high purity germanium? That is a semiconductor. We will be talking about it. Click scintillators have been studied to good light yield and good pulse rate discriminancy. What are its disadvantages? I'm not super familiar with Click. However, I do know that Click it's continuously being studied, and I have some colleagues who are working with it. I'd be happy to get you in touch with them. What do I mean by hygroscopic? I mean just sensitive to moisture in the air. Next, we have BGO, or bismuth germanate, BGO. And this has a very high Z, making it very, very efficient at high energy photoabsorption, and it's non-hygroscopic. So it's a very useful scintillator, and I know people are working on this quite a bit. Then last one is lead tungstenate, has a very high Z. It's faster than BGO, and it was used by ALICE, a large ion collider experiment at CERN, to study these lead-lead interaction collisions. So there's one application of one right there. I am running out of time, so I'm going to move on. I'm going to skip this slide. All it is basically just how sodium iodide detectors are made. Pretty straightforward. The idea is then when you apply this sodium iodide detector here, you have this gamma ray source, let's call it cobalt 60. The gamma ray enters the photomultiplier and it gets the digitation. And what we get is a spectrum of events here. So you can see the horizontal axis is the channel number. It corresponds to the energy of the incident photon. And the vertical axis is counts. So this is just a histogram. And you can see there's two sort of characteristic mounds here for these sodium iodide detectors. It's very useful. This corresponds to the 1.1 MeV and 1.3 MeV detector. I saw there was a question. I'm sorry I can't answer it right now. Um, Thank you. Um, if we have questions, I can stick around a little bit at the end and go back to some of these, but I don't want to take up too much more people's time because I'm only allotted an hour. So what we get is a gamma ray spectrum. This is what I think of when I think of measuring gamma rays, is making a spectrum of all of these. So this is the cobalt 61. And I want to really talk really fast about these two peaks because you see that there's these blue lines that are very narrow versus the more broad red peaks. This sorry, is the idea of energy resolution. It's a detector's ability to distinguish interactions at different energies. That's crucial. And they're characterized by a full width at half maximum of the peak. So if we have this nice Gaussian distribution here, and we want to know its full width at half max, what we can do is take the maximum value, find where it's at a half, and then find the range of x values that is the range here. And that is what is corresponding to the full width at half maximum. So that is how we define energy resolution in our measurements. We have scintillators, which have an energy resolution of about 20 to 500 EV per photoelectron. So pretty broad, full width half max. Gaseous detectors have about 30 electron volts for one electron ion pair. However, again, you have to be aware that the fill gas is going to change that a lot. And then lastly, we have semiconductors. And I really want to point out semiconductors here because semiconductors have a range of 3 to 10 electron volts for one electron hole pair, which is still 10 at its upper bound compared to 20 at the lower bound of scintillators. So if you're doing spectroscopy, for example, which I saw someone posted earlier for an application, if you're doing spectroscopy, scintillators are only okay at it compared to semiconductors. Because if you use a semiconductor detector, like high purity germanium, you can see that you get a much more narrow peak, especially right here. The blue line is that high purity germanium peak versus the sodium iodide peak. And as you can see, there's like no broadening here, dude. Versus here, where there's a whole range of potential energies we could have. So that's the strength of a semiconductor compared to a scintillator or an inorganic scintillator. Now, I'm going to talk a bit more about semiconductors here. This is sort of the last major topic I'm going to cover. So these are, again, very complicated. I'm going to explain the band gap in a little bit more detail with a bit of an analogy, and then talk about some of the things that I kind of use. So the semiconductor principle worked very similarly to like those inorganic scintillators, where you have a crystal lattice structure and a band gap. And the idea is that in order to create an electron hole pair, you have to have a photon that has enough energy to create an ion. If it doesn't, it just won't create one. It's kind of like Homer Simpson skateboarding the Springfield Gorge, where if you start at a low height and you don't develop enough velocity to jump the gorge, you're going to fall down and you won't make the other side. It's sort of like running, jumping, and landing and going, I fell down here. Versus if you have enough speed, you can make that jump. That's kind of an analogy. I'd be happy to explain it again later. I realize I'm moving very fast. Um, the idea is that this band gap is something that is material dependent. Does that make semiconductors the best to use? That's a good question because sometimes you don't need all of the things that come with semiconductors. And I say that because high purity germanium detectors have a band gap of 0.87 electron volts, I want to say. And so that means that smaller band gaps are prone to creating electron hole pairs from thermal energy, which is not good. That's like electronic noise. We do not want that. And so high purity germanium detectors need to be cooled to cryogenic temperatures with liquid nitrogen in order to get that spectrum that was really, really precise. So if you can use high purity germanium, maybe you want to do that, but maybe you don't. There are a variety of applications for scintillators and ion chambers. Excuse me. Let's put it this way. Scintillators and ion chambers still see commercial use despite that semiconductors do provide very high resolution energy spectra. So think about that maybe. There is demand and use for all of these on the market. And that sort of goes back to the idea of thinking about the applications of all of these. So there's types of semiconductor detectors, much like how there were with inorganic scintillators that were doped with some extra material. You can provide some impurities to making jumping the band gap easier. And that depends on the specific dopant that you apply. So if you have a group 3 element like boron in this detector, you sort of create an acceptor site for an electron. Versus if you have a group 5 element like phosphorus, you might have a donor electron. So it can provide an electron somewhere else. These are known as p-type and n-type semiconductor detectors. There are also intrinsic detectors that are intrinsically semiconducting. However, these are hard to achieve in a practical sense. They are possible. It's just they cost a lot to make, and any imprecisions or any issues in the detector yield poor results. So we want to keep that in mind. So I'm going to talk really quickly about two common semiconductor detectors. As I've alluded to a lot through the last section, there are high purity germanium detectors, or HPGE detectors, which are sort of these gold standards in semiconductor radiation detectors. What I mean by that is they can achieve extremely good energy resolution, like 0.2% energy resolution for the calibration peak of cesium 137. This is the 662 keV peak, if you've heard of that. And think about it, zero point 0.2 of 662. That's like 1 K, that's like 1 keV at most on either side in this spectrum. So very little deviation. The problem with high purity germanium detectors is that they need to be cooled. So you're trading off really high resolution measurements for a lot of mass. And so if you want to use if you want to get high resolution gamma ray spectra measurements in space, for example, right? One of the limiting factors of space applications is mass. And so high purity germanium detectors add a lot of mass to a payload if you're sending it up into space. So that might not be the best detector to use there. Just a thought. What I work with, finally, is I work with cadmium zinc telluride, or CZT, radiation detectors. These are well developed room temperature semiconductor radiation detectors. They have a band gap of approximately 1.6 electron volts, meaning that they can be operated at room temperature, and they are approaching that zero point 0.2 energy resolution limit. Um, right now it's approaching the zero point 0.3 in research settings, but typical commercial CZT detectors regularly get like 0.5, 0.6, 0.7 energy resolution for that 662 keV peak. So that is a great alternative in this case. And now instead of like an entire jug of liquid nitrogen, you only have to send this detector up into space. There's a detector like this going up into space next year. So very, very fun, very cool. Again, my area of expertise is working with these. So if you have specific questions about that, I can answer them to the best of my abilities. The one, which of the semiconductor detectors is best for irradiation? That is a tough question because there's a lot of. I don't quite know what you mean by that. I do know that you can sort of recover damage from radiation detectors through various crystal treatment processes, but that's beyond my area of expertise right in this talk. So we'll, if you have, yeah, I'd say keep that question in mind and maybe read some there's text I'll provide to you in a moment. The problem with the CZT is it's expensive to manufacture. Cadmium, zinc, and tellurium, all very rare materials, and it's difficult to grow these crystals beyond the sizes they are now. So that's kind of a limiting factor right now, but there's obviously continuous improvements to all of these detectors. I'm doing research on these, so obviously like they're always going to be there's ways to improve them further. So with that, I have just some final remarks. When choosing a gamma detector, one must consider the why, the application. Are you trying to identify a radioactive source? Are you trying to know how much of the source there is? Are you trying to verify what this work is doing? Um, what is the research being done? I will answer the question in the chat here. What is my precise work with CZT after I finish this? Because I'd be happy to talk about that. The source characteristics. What is the source you're trying to measure? Is it what energy is it? What activity is it? What is it made of? Is it more than one source? The geometry of the detector and the source. Where is it put? The detector material, the effective Z, the light yield, or the decay times, or amplification needs, what you expect from a signal. Is there going to be dead time? Are you expecting a high flux of radiation? And as a result, you have to make sure the electronics aren't overwhelmed. And to that end, associated electronics. What are they? What is the digitization or the readout? And like, how much does it cost? At this point, all the questions that are in the chat, I will answer at the end of the presentation. So please stick around. Lastly, in academia, we often consider reading and literature and forums and communication and talking with others and learning from others in spaces, from great thinkers in the field, whatever field it may be. And I have here the School of Athens painted by Raphael in 1511 at the Vatican City. And you have here two dudes, Plato and Aristotle. And look, they're carrying books, right? What books do you think they might be carrying here? Perhaps they are carrying Radiation Detection and Measurement by Glenn Knoll. Glenn Knoll, soft spot, Michigan, got to represent it, wrote the book on radiation detection and measurement. The idea is that all of the content that I have presented here in this talk can be found in this book, and I would highly, highly encourage you to read this book or go through it if you want to know more in greater detail. It's a very readable textbook. I have read my fair share of textbooks as a grad student, and I think, beyond the fact that I'm doing research in this field, this book is one of the best textbooks I have read when it comes to really getting at the foundations of the physics while still making it approachable. And Glenn Knoll here was actually a mentor of my own research advisor. So we have a little shrine dedicated to him in our lab. It's very fun. But would highly recommend you go out and find this book. The newest edition is the fourth edition, and I really hope that you take some time to maybe read this. Shout outs again to the University of Michigan, where I'm from, and I want to put it out here very quickly for the YouTube video. This is the fair use disclaimer. This presentation was made for educational purposes. Copyright disclaimer under Section 107 of the Copyright Act of 1976. Allowance is made for fair use for purposes such as criticism, comment, news reporting, teaching, scholarship, education, and research. Here's the bibliography. Here's some of the sources that we consulted. Glenn Knoll, Radiation Detection and Measurement, 4th edition, published by Wiley and Sons in 2010. Really, really important, really useful. Image attributions, here they are. You can't read them. Thanks for your attention. That is the main bulk of the talk, and it's 1:57. I got through it. I was worried we were going to run out of time there. Thank you for your attention so much. I will be answering questions in the chat now, but at this point, that is the end of the presentation. And there's one question: can a high schooler read this book? I would say it might be a little challenging, but I think you can do it because the book covers beyond the photon interactions. It starts at the very beginning of like gamma ray interacting with matter, and then it talks about statistics and counting statistics. And that I believe is just as important that I didn't talk about at all in this talk is the idea of statistics. I think that the book is really useful. I think undergraduate students should be able to have a good time with it. High school students, you might have to spend a little time with it, but you know what? You're here at this talk, you're curious, you're interested. Try it. Why not? You know what? If it is too complicated, you'll probably grow as an academic at some point and you'll come back to it. And I think that that's really important. Just because maybe you don't understand something immediately does not mean that you'll never understand it. I'm wrapping up my third year of grad school. I've been in academia since 2016. So I want you to know that I was where you all were at one point. So I would definitely say take that time, struggle with the material, try to understand it. But if you don't understand it, that's okay. Anyway, at this point, I'm going to answer some of the questions. Again, I don't know, Skylar, Courtney, are there any things you want to say before I take questions?
I just want to again thank everyone for attending. Thank you, Peter, for the great talk. Like I said, or like Peter said, we'll be going over some more questions if you want to stick around. Um, but yeah, Peter, you going to sift through some of the questions you really enjoy.
Yeah, starting from the top, I have from Tiwari, last name. What are your precise work with CZT detectors? Just trying to understand its application. So, in my group, we are working continuously on finding ways to advance uses of CZT. So, for example, I work with CZT under high gamma ray flux and high energy environments. So, I'm working on measuring gamma rays up to like 10 MeV. Presently, CZT detectors operate pretty well up to about 2 or 3 MeV, but they haven't been characterized with regards to like detector efficiency and the system response, i.e., what do we expect to measure when we measure it with this detector? That's a lot of what my work is going into.